C.O and C.1. So this lesson is going to be probably half introduction in terms of like administrative things, and then the other half will be actual content, and then we'll progress throughout the booklet.
Okay.
Do you have any questions?
No.
All right, cool. Do you wish to get the C.O booklet out just so we can kind of go through how everything works?
Yeah, I got it out now.
All right, no problem. And one thing I want to ask is, how are you going to write in these booklets? Are you going to print them out, or do you have like a stylus?
I guess I'll print them out.
Okay.
Yeah.
Because I just have a stylus, so I just kind of write on the screen, if that works. Okay, cool. So, all right, so if you get it out, you will see the course structure. So this is essentially what we're going to be covering. So obviously you have your table, year 12 is 120 hours, and year 11 is also 120 hours. There are 8 modules, and although NESA says 60 hours, it's like meant to take a turn, in reality we will cover probably a module in about 7 to 8 weeks on average.
Okay.
So when C.1 booklet, once we kind of get through the admin stuff, you'll see that there's actually a lesson timetable. And in terms of theory, I would finish each module in about 5 weeks, so half a term. And then we typically do 2 weeks of revision, 1 week of the end of module exam, and then 1 week going over that exam before we continue.
All right.
Does that make sense?
Yeah.
All right, cool. So there's 8 modules, as I said. They increase in difficulty to an extent. I'd like to point out in particular is that you may have been led to believe that Year 11 content cannot be assessed in Year 12. However, that is not true. You can absolutely be assessed on Year 11 content in your HSC.
Okay.
And I know this from first-hand experience. So I was the first cohort to go through the new syllabus.
Oh, okay.
Yeah, so I was the guinea pig.
Yeah.
But yeah, so now I get to kind of share my experiences, kind of see how it is. Chemistry was very straightforward, no surprises. So you should be pretty good.
Okay.
Cool. And then, yeah, Year 12. So are you aware of the changes to assessments in Year 11 and 12?
Not exactly.
Okay, so the changes to assessments is that in Year 11, you can only have a maximum of 3 assessment tasks, and in Year 12, you can only have a maximum of 4 assessment tasks.
All right.
So what that means is that in Year 11, you're going to have your prelims, and then you're only going to have 2 other tasks.
Oh, okay.
Yeah. So, and also, any formal exam is capped at 30%.
Oh, okay.
Yeah. So that means that it's really stupid. I questioned it when I was there as well. How it actually works is that you have, well, 30% for the prelim, and then there's 70% left over. So in between 2 tasks, so you're going to have a task that's actually worth more than your preliminary exam.
Oh.
Yeah. So for me personally, I remember so the reason why I'm bringing this up is because of practical investigations. So because you're doing a science and because they can't actually give you an exam, what schools now resort to is giving practical exams.
Right. Okay.
Yeah. So in Year 11, my first task, it was an experiment. I'll outline what the experiment was once we get to that content. That was worth 30%. My second assessment task was another experiment that was worth 40%, and then the preliminary happened.
Oh, that's weird.
Yeah. So, yeah, one of the new things regarding the new syllabus is that they don't necessarily want to make it cookie cutter so that everyone can just walk in memorizing the whole textbook and get full marks.
Okay.
Yeah. And also one last thing about practical investigations, you will be expected to remember and revise certain practice that you have done in your exams.
Right. Okay.
Yeah. Do you have any questions so far?
No.
Okay, cool. This is all like new to you, is it?
Yeah.
All right. I actually already went over assessments, assignments, exams, and assessments, so we can go to depth studies. So do you know what a depth study is?
No.
Okay, so a depth study is kind of just this fancy term that NASA have coined for the sole purpose of giving the excuse of giving you a really, really big assignment.
Right. Okay.
So an example of a depth study, so I'll relate to my depth study, was in year 12 physics. I had to build an electric motor from scratch.
Oh my gosh.
So yeah, so it may not necessarily be big, but it's an assignment that's genuinely is meant to take a turn. And the idea of the depth study is you actually do your own research.
Right. Okay.
Yeah. But however, so this is where it's all like up in the air. Many teachers use the depth study as an opportunity to stop teaching you. Because what they can do, they can give you a topic that you're meant to be covering, but you research the topic yourself.
Right. Okay.
So that's kind of where I come in. So I will obviously, well, I aim to properly teach you how everything works.
Yeah. Okay.
Yeah, the requirements of depth studies is just all copy paste from NES's site. On the next page, you can see some ideas of depth studies. So these could be things that they can ask you to do. So this is all straight from NASA. So this is not my personal experience. This is actually what NASA have said you can do.
Right. Okay.
Yeah. But the whole point is that they're meant to gather the other scientific skills. So have you heard of the scientific process?
I have. I don't know what it is though.
Okay, the scientific process is essentially a way of thinking that scientists develop. So, for example, I'm studying physics at university. I wish to get my PhD. So, the thinking that you have to do, well, develop rather, is being able to propose a question, then research that question, create an experiment, do the experiment, see if your experimental results are in line with your theoretical results. If they are, perfect. If they aren't, well, try again.
Okay.
Yeah. So
Right.
I understand that this all might be a little bit unfamiliar to you, but we will cover all these things. Don't you worry.
Okay.
Okay. Go to page 6. So page 6 is actually where the actual introduction content, well, not syllabus content, but science content is.
Right. Yep. I'm on it.
All right. So do you know how to write a scientific report?
I do. Yes.
Okay. So you know that we have our aim,
Yeah.
and then the hypothesis, the equipment list, the risk assessment. Have you written a risk assessment before?
Yeah.
Perfect. Do you know how to draw all the equipment in a scientific diagram?
Yeah.
Perfect. I'm only asking because I've had students that haven't, so I've had to kind of go over it. Okay, and also we have our analysis and discussion. So I trust that you know what accuracy, validity, and reliability is.
Yeah.
Perfect. Can you please tell me what each of them are?
Accuracy is, well, oh, I can't define it without saying the word accurate. um,
That's okay. By all means.
well, basically, it's whether your results are um, uh,
Let,
accurate.
let's Yeah, replace the word accurate with close to.
Close to. Close to your, I guess, hypothesis, what you hypothesized.
Perfect. So a little bit more concise than that, it is the closeness of your experimental to your theoretical.
Right. Okay.
Can you tell me what reliability is?
Yeah. Reliability, it's basically whether all your results are similar. Therefore, your conclusion will be reliable, I guess.
Yeah, I guess.
Yeah.
But don't worry, when we do experiments, you'll absolutely know them off the top of your head.
Yeah.
So you got the first part right. If your results are close together, that implies that the experiment is reliable. But if your results are close together, that means that your apparatus, so everything that you're doing in the experiment, is doing its job properly.
Right. Okay.
There's random results in there. There's no massive outliers that can affect things like the average.
Okay.
Is this all familiar to you?
Yeah. Yeah.
Okay, cool. If I say something that's not familiar, please stop me.
No, that's fine.
All right. And thirdly, what about the validity of the experiment?
It's basically whether the 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 measurements you're measuring are what it should be.
Not really. Validity is a measure of how well your experiment addresses your aim.
Right. Yeah. Okay. Yeah,
So,
that's
so for example, if I am measuring the boiling point of water in an experiment, would I use my finger to test the temperature?
no.
Well, that's not valid because how can I know what the temperature is?
Yeah.
So we with equipment like a thermometer that actually gives us what we set out to do.
Okay.
Does that make sense?
Yeah.
All right, cool. Do you have any questions?
No.
Okay, perfect. So if we go to the next page, we're going to go over some very important terminology regarding like results. So this is just establishing background. It seems in this document, so when I capitalize something, I also bold it. So those like you measure, they're meant to be bolded. So you can bold them if you like.
Okay.
But so are you familiar with all these terms?
Yeah.
All right, perfect. And there's also a definition of validity, reliability, and accuracy.
Yeah.
So in particular, I would like to focus on accuracy because accuracy is actually something that we can quantitatively define.
All right.
And the way that we can quantitatively define this is through something called percentage error.
Okay.
What the percentage error is, it's the difference between your theoretical value and your experimental value over your theoretical value times 100. So that is that value there. And I'd like to provide you with an example quickly. So I will share my screen to my whiteboard. So let's say that we're doing an experiment, and let's say that the theoretical mass of my stylus is, I don't know, 68 grams. Yeah. And let's say that I measure it on scales that haven't been properly taired, and I end up getting a mass of 64.2 grams. That one too. 64.6. So if the percentage error, all this is saying is, well, how far off am I in terms of the percentage? Does that make sense?
Yeah.
Cool. And we can see that this was 5.3% off. So that means that
Okay.
we were 94.7% accurate in determining what the actual weight was.
Yeah. Sorry, something fell.
All good. So does this make sense?
Yeah, it does.
All right, perfect. And then we also have something called the degree of accuracy. So the degree of accuracy is just how close we were to the results. And the degree of accuracy is just whatever makes this 100. So that means that we were 94.7% accurate in this experiment.
Okay.
These two should add up to 100,
Yeah.
which makes sense. Cool. So this brings us to something called the limit of reading. Have you heard of this before?
No.
Okay, cool. If you go to the final paragraph on page 10, it will say it's limit of reading is bolded. But what the limit of reading is it's based on the idea that the accuracy of an experiment, so how accurate your results are dependent on how accurate your equipment is. So for example, if I am measuring a length, actually has an example here. If I'm measuring a time with a stopwatch and then I measure a time with a light gate, what is going to be more accurate?
The stopwatch.
The light gate. Have you
Oh.
used the light gate before?
No.
Okay. What a light gate does, and I don't think you will come across these, but we'll use a ruler example. So if I'm measuring a length with a ruler, and it's a 30 centimeter ruler, well, my limit of reading is going to be in centimeters, isn't it? So that means I can measure, the smallest measurement that I can do is a 0.5 millimeter. Does that make sense?
Yeah.
Because if you look at your 30 centimeter ruler or whatever you have in your pencil case, we have these very fine markings. And when you measure it, you can say that something is, I don't know, 15.3 centimeters because we have millimeters. However, this is technically to the nearest millimeter, isn't it?
Yeah.
Yeah. So this is where the idea of error comes in. So technically, we would write the measurement being 13 point, I'll just do 13.2 plus 0.05 centimeters. Now, this you're probably like, where the heck did this come from? Well, because this is to the nearest millimeter, that means that we can be off by 0.5 millimeter because we round that 0.5 millimeter, don't we?
Yeah.
So this is, you'll never actually have to write the plus or minus. I'm just kind of demonstrating my point. The plus or minus is more of a physics thing. But this is called the limit of reading. So the limit of reading on your ruler is 0.5 centimeter, 0.5 millimeter. It's going to be half of the smallest measurement you can make.
Okay.
Whereas, do you know what a caliper is?
No.
Okay, a caliper is a device that engineers use, and it kind of is like that, like an F. And there's an actual computer that measures the distance between these 2 points. So all that means is that the caliper is more accurate than the ruler. So therefore it has lower limit of reading, so therefore it's more accurate.
Okay.
That's all I'm trying to refer to here. So the limit of reading is literally the limit of how accurate a piece of equipment can get.
All right. Okay.
Yeah. Do you have any questions?
No, that's fine.
All right, cool. If we go to the next page, I trust that you know how to draw a graph.
Yeah.
All right, perfect. So I won't get you to do that. You know how to calculate the gradient of a graph?
Yeah.
Perfect. Do you know significant figures?
I have done it. I haven't done it in a while though.
Okay. Would you like to refresh it, or would you just like me to go through the theory?
Refresh, please.
All right, no problem. So let me explain why we use significant figures in science first. Essentially, the whole point of using significant figures in science is because none of your measurements are going to be exact. They're always going to be grounded because of the limit of reading, just like the ruler earlier.
Okay.
So we use significant figures to kind of combat the rounding that we use in our questions. So the rules of significant figures are the 4 dot points. So non-zero digits are always significant. A final zero or trailing zero are always significant. Any zeros between two significant figures are significant. And the big one, and this is the one, you can actually lose marks for this if you don't have it properly. In any science, you must always leave your answer with the significant figures. If there are a different number of significant figures for quantities, you must pick the one with the least. I know it says most, but I am correcting it. It's least number of significant figures.
Okay.
So what does that mean? Well, if I give you a question and I'm just pulling measurements out of the sky, and let's say distance, so d, distance, speed. Okay, cool. So if I were to give you these 3 measurements, so we have distance, time, and speed, can you tell me how many significant figures are in each of these
In distance, there are 3 significant figures.
Perfect.
And in time, there are 5 significant figures.
There's 4.
4.
Yeah. The 0 doesn't count.
Okay. All right.
Okay, let me change the question. What if this was a 0?
There'd still be 4.
Perfect. And what about the last one?
There are 2 significant figures.
All right, good. So if I gave you a question and you did some calculation that involved speed, distance, and time, how many significant figures would you leave your answer in?
2.
Perfect, because that is the lowest number of significant figures in the question. And
Yeah.
hence, that is the guaranteed, so this, damn it. That was meant to say most. Yeah. So in this question, 2 significant figures is guaranteed to be the most accurate.
Okay.
Do you have any questions?
No.
All All right, cool. We'll move on. You can do that concept check if you like. I don't particularly mind.
All right.
On the next page, do you know how to do scientific notation?
Yeah.
Hello?
Yeah, I can hear you now.
Okay. Do you know how to do scientific notation, to write your numbers in scientific notation?
Yes.
All right, cool. There's a concept check if you wish to do it. I don't particularly mind. Prefixes aren't really involved in chemistry to an extent. And then the final thing that we'll be covering is going to, before we begin actual content, is going to be on page 17. So in chemistry, there are quite a couple of skills that you need. And a lot of these, well, a good number of these skills are mathematical skills because we often engage in several equations when we're trying to find things that we want in chemistry.
Okay.
So, yeah. In the sciences, chemistry in particular, is that these courses are designed for students from all backgrounds in mathematics, from Extension 2 all the way to Standard. So may I ask what mathematics you're doing?
Extension 1 and advanced.
Okay, cool. So you'll be pretty, you should be pretty comfortable.
Yeah.
So the idea is because there's no prerequisite for math standard kids can get into it, which means that the mathematics isn't going to be very difficult.
Right.
Yeah. And then finally, most formulas and equations that you will encounter within chemistry are displayed on your formula sheet. Do you have a copy of the formula sheet? I can send it to you now.
Yes, please.
No problem. Let me just get it out. All right, cool. There you go. So there's a copy of your formula sheet. It's nothing too flash. There's a lot that you won't be able to answer yet because, well, we kind of just started. And we'll just kind of go along.
Okay.
So there's a concept check. There's equations I don't particularly mind once again. And that brings us to the syllabus. So I kind of included the syllabus at the end of the introductory lesson, because, well, it's meant to be half. And here's essentially just a checklist of the syllabus in case you didn't have it.
All right.
One thing that you may wish to do is every lesson, when we do something, you can come and tick off the dot point so you know what we've done and what we're yet to do.
All right.
That's essentially it. Do you have any questions? Is there anything you want to kind of go over? Are you kind of content with the administrative parts?
Yeah, I'm all right. Hello?
Can you hear me?
Yeah. No, I said I was all right.
All right, so that finally brings us to the content. So you can get C.1 out now.
Mm-hmm.
We'll do this. So this module is called Properties and Structure of Matter. It's an introductory module just to kind of familiarize you with what you're going to be learning in chemistry.
Okay.
So the first lesson, well, the first dot points that we're going to be covering is, so at the top of every new dot point that we start, I have the respective dot points. I may do things a little bit out of order, but I will do things out of order only if the sequence is better doing it this way.
All right.
Yeah. So firstly, we're going to look at physical and chemical properties. So the physical properties of a substance, so this is actually beginning theory. The physical properties of a substance are the characteristics that, I'm just reading, that we can observe or measure without changing it into a different substance. So the example that I gave was ice and water are two different states of the same substance. Hence, the melting point of water is a physical property. So essentially, if the physical properties of something is what it can do without changing into a different substance.
Okay.
So what some physical properties are?
Sorry, could you repeat that?
No problem. So the physical properties of a substance, you may be able to hear me better. The physical properties of a substance are essentially the properties that are innate, so they belong solely to that substance. And if that substance were to change into another substance, it would have different physical properties. So for example, we have ice and water. So they're the same substance, but, well, one's been frozen. But if I were to mix salt and water, the melting point of water is different.
Okay.
So what do you think some examples of physical properties are?
Mm, would cooking be an example?
What do you mean by cooking?
So, like, if you're just making a meal out of one type of food, and then another meal with that type of food along with others, is that kind of
Not really.
not really? Okay.
So another example of a physical property, well, we have melting point. So we're going to have freezing point. Well, freezing point is free, yeah. Melting point, and we have boiling point.
Okay.
Because another random liquid, let's do petrol, which is octane. Octane, so petrol, has a different boiling point to water. Another example of a physical property would be the color of water. They're things that are specific to water. Yeah, so what do you think another physical property would be?
All right. So there's temperature and color.
Oh, well,
Yeah.
melting point, boiling point, and color.
Melting point, boiling point, and color. Uh, the consistency.
Not necessarily.
Okay.
So another one is, are you familiar with density?
Yeah.
Density is how much mass is in a certain volume. So for example, the fact that water weighs 1 gram per cubic meter, you are familiar with that, yeah?
Yeah.
Yeah, is density, because aluminium, actually no, steel, for example, 1 cubic meter of steel weighs 7 grams, 7 kilograms.
Okay.
So once again, physical properties are things that are specific to that substance.
Oh, all right. Now I get it.
So you can, all right, cool. So do you think you got it now?
I think I'm
All right.
struggling to think of examples though.
Okay, just shoot, whatever.
Um, Mm, oh, I don't know.
Okay. Another one would be its smell. What does water smell like?
Yeah.
What would be another one?
What does it taste like?
No, that's completely legitimate. Yeah, that's one.
All right.
Give me one more.
Does sound? No, not
Oh,
really.
not really.
Yeah.
Nah, because sound isn't really a property. Sound is like, so like for example, if you have so like my bottle of water, is my bottle of water making a sound at the moment?
No.
So yeah, we can't really use that one.
Yeah. Okay. Would it
So
be its texture?
yeah, that would be one.
All right.
Yeah. So they're essentially physical things, hence physical changes or physical properties. Yeah, so they're physical things that we can actually measure. So like I can actually measure the boiling point. I can measure the melting point. I can measure its smell, technically. I can measure its density. I can measure its taste. I can measure its texture even. Just things that we can physically measure. They are the physical properties.
Yeah.
Cool. So now we're going to contrast that to chemical properties. So whereas a physical property are the properties of one substance, water in our example, the chemical properties of a substance are those that arise when something reacts chemically.
All right.
So so an example, so we don't necessarily go over chemical properties yet because we're going to do it a little bit later, but an example of a chemical property is how a substance reacts with water.
Ah, okay.
So like, for example, salt dissolves in water, but however, there's some molecules that don't dissolve in water and things like that.
Oh, all right.
But this is all just really new, like beginning of the stuff.
All right.
Yeah. So what this first dot point is talking about in particular is the idea of mixtures. So the reason why I'm talking about physical properties and chemical properties is, well, the syllabus mandates it, but also because we're going to use the knowledge that we have just acquired to find out how to separate mixtures. So
Okay.
what is a mixture? Well, as it says here, a mixture is a combination of two or more pure substances. So pure just means it's pure, is like liquid, pure water is just H2O.
Mm-hmm.
Um, it's mixed in a mixture, each substance retains its individual chemical properties. So what does that mean? Well, water isn't an example of a mixture because water is pure on it by itself, isn't it?
Yeah.
But an example of a mixture would be salt water. Can you tell me why salt water would be a mixture?
Um, well, the salt retains its chemical value
Mm-hmm.
set in this, and the water is not
Yeah,
separate.
that's essentially it.
Yeah.
Yeah. Well, you hit it on the head. The salt retains its chemical properties because it kind of dissolves in the water. It doesn't really
Yeah.
react with the water, does it?
Yeah.
You can still get the salt out of the water if you wish.
Yeah.
All right, cool. Now, one thing that we're going to look at is that there are two types of mixtures. We have heterogeneous and homogeneous. So how I like to remember the differences between these mixtures is by the prefix. So typically homo means same, whilst hetero means different. So what is a homogeneous mixture? Well, a homogeneous mixture basically means basically occurs when the two substances are completely mixed in with each other.
Yeah.
So an example of a homogeneous mixture is salt water. And as we know, we can get the salt back out of the water by exploiting the physical properties of each component of that mixture.
Yeah.
All right, cool. A heterogeneous mixture is an example of a mixture where we have two different states of matter. So this is the main difference between heterogeneous and homogeneous. Homogeneous mixtures have the same state of matter. So you might say, oh, but hang on, you just said salt water, but salt is solid. Well, as we're going to find out in a bit, salt actually becomes aqueous, so that's the actual term we call it, when it's dissolved in water.
Okay.
Have you heard of aqueous?
Yeah.
Okay, cool. So that's a homogeneous mixture, whilst a heterogeneous mixture is one where we have two different states of matter. So an example of a heterogeneous mixture is rocks and water.
Okay.
Do you have any questions?
In heterogeneous mixtures, do the substances have to be in different states?
Yes.
Okay.
Yes. So like, for example, a homogeneous mixture would be cordial.
All right.
Because the cordial mixes in with the water. But a heterogeneous mixture would be milk and whipped cream.
Okay. All right.
The whipped cream is solid and milk is liquid.
Okay. So technically, before the salt and the water are mixed, at first would the mixture be heterogeneous, and then once you stir it and once it's completely dissolved, it will be homogeneous?
Perfect. That's 100% correct.
Yeah. Okay.
Yeah, excellent work. All right. So now that we kind of know the difference between homogeneous and heterogeneous, and we know about chemical and physical properties, we're going to use our knowledge to kind of separate mixtures now. So the first one that we're going to do is boiling point. So the boiling point of a substance is defined at the temperature at which it evaporates from a liquid to a gas. So the most common boiling point experiment that you may do, I don't know if you'd actually do this, but we can distill alcohol from water. Do you know what distillation is?
Yeah.
All right, perfect. So the reason why we can distill alcohol from water is because alcohol has a lower boiling point than water. Alcohol has a boiling point of about 79 degrees.
Okay.
So hence, if I boil the alcohol away and I distill it, I've separated the alcohol from the water.
Oh, okay.
Cool. So this actually occurs in evaporation and distillation. Do you know the apparatus regarding distillation?
No.
Okay, so I'll just kind of read this paragraph. So evaporation and distillation involves setting up a Bunsen burner and the solution in either a beaker, which you would use in evaporation, or a distillation flask. So when you distill something, you actually need to use the proper. So in evaporation, the substance with the lower boiling point is vaporized, so it just means turned into a gas, and it escapes because there's nothing holding it in.
Yeah.
But in distillation, the vaporized gas is trapped and is placed through something called a condenser, where it turns back into a liquid. So this is the apparatus here. And this apparatus, this very same image, was used in my preliminary exam in year 11. It was actually the first writing question. It was question 21. You had to label all the parts.
Oh, okay.
So essentially, what a condenser is it's like a tube, and the tube is kept very cold by running water in and out of the tube, as you can probably see.
Yeah.
And well, if it's cold, that means that the gas is going to turn back into a liquid, so it condenses.
Yeah. Okay.
Yeah. So that comes from the idea of condensation.
All right. Yeah.
I asked, do you have any questions, and you said
Oh, no, sorry. I didn't hear that. No, I don't. That's fine.
All straightforward so far?
Yeah.
All right, cool. So the next thing that we're going to look at is fractional distillation. So fractional distillation, I have seen it in textbooks, but I personally didn't cover it in class, so I thought I may as well just put it in here. So what fractional distillation is what happens if I have a mixture of more than two liquids. Let's say I've mixed alcohol, water, and what will be a third one? Alcohol, water, and let's say mercury. Mercury is a liquid at room temperature. Did you know that?
Yeah.
All right, cool. So let's say I've mixed three liquids together. How would I remove all of the three liquids from each other?
I guess the same way as the diagram shows. So the substance with the lowest boiling point, which is alcohol. Is it?
Mm-hmm.
Yeah. Would evaporate first, and then it will be condensed, and then all the substances will be separated.
Yeah, perfect. So that process that you just described is called fractional distillation. So this is on the next page.
Okay, yeah.
So fractional distillation is a process, just how you described, where we extract things that have different boiling points.
Right.
So fractional distillation is typically seen through the distillation of crude oil. So you will see this. I believe you might do an experiment on it, but I know you absolutely cover this in Year 12. And it's essentially we pass the crude oil in, and the things that have the lowest boiling points, they're at the top because they heat up very quickly and they turn into gas.
Yeah.
Whilst the things that have a very high boiling point, they stay at the bottom.
Oh, okay.
And that's kind of how they turn crude oil into all the various products that we use in our lives.
Right. All right.
Do you have any questions?
No.
All right, cool. So if we go to the next page, we're going to continue with particle size. So the idea of exploiting particle size comes from the obvious fact that different substances have different sizes, and we the property of particle size through using a sieve or a filter to separate mixtures. So a typical example that everyone uses is using a colander when making pasta.
Yeah.
Obviously, the pasta is not as small as the water, so the water escapes and the pasta is left behind.
Right, yeah.
So what this actual technique is called filtration or sieving. So I'll read this and then I'll go over the differences. Oh, actually it says it here. So sieving, it simply just involves passing the mixture through an instrument with many holes, such as the colander in this example above. But filtration is a little bit more complicated, where we actually use something called filter paper. And filter paper is an actual scientific piece of equipment that is waterproof, typically, and has very, very fine holes. So it's so fine that it can stop things such as sand from getting through.
Okay. Yeah.
Have you come across filter paper before?
Yeah, we've used it in experiments.
All right, perfect. So you'll be familiar with this.
Yeah.
So this is our kind of this is the diagram, and we can kind of see, well, you can see on your one how in conjunction with the filter paper we use a filter funnel, and also you must note that whatever is left behind in the filter paper is called the residue, whilst the liquid that has been filtered through is called the filtrate.
All right.
Do you recall this?
Yeah.
All right, perfect. All right. Another property is magnetic, so magnetism. So if a component of a mixture is magnetic, this property can be used to separate the mixture. For example, magnetic iron can be separated from sand using magnets.
Yeah.
Make sense?
Yeah.
All right, cool. The next one that we're going to do is density. So I kind of spoke about density before. So density is the idea of the mass per unit volume. So how much something of a certain volume weighs.
Yeah.
So the most obvious example that you will probably do is oil and water. So oil is less dense than water, and then hence the oil floats above the water.
Yeah.
And it can be separated through a process known as decantation. So what decantation is essentially just pouring off the top liquid.
Okay. Yeah.
So the second one that we're going to look at is called sedimentation. So what sedimentation is when you make a saltwater solution, if you leave it for a long enough period of time, the salt settles at the bottom of the water, doesn't it?
Yeah.
This is because the salt is more dense than the water. And well, things that are denser tend to sink. So it forms a sediment at the bottom of the container.
Right.
Do you have any questions?
No.
Okay, cool. And then there's also centrifuging, but that's not really a Year 11 one. So what a centrifuge is, it's a spinning machine basically. So this could be my liquid, and it will just go like that for a certain period of time. And what it does is it actually speeds up the separation process by density.
Okay. Yeah.
So if I were to, this is salt water, and if I were to spin it around, it may have been completely mixed initially, but when I get it out, you actually see the salt settled at the bottom.
Okay.
Because it uses forces and things from physics that you don't really need to know.
All right.
Do you have any questions?
No.
All right, cool. And I know it kind of goes on for a bit, but we will essentially get to a concept check on where we can actually showcase your knowledge. So these are all just a different type. So the next one is separating immiscible liquids. So two liquids are said to be immiscible. So all this means is that they're a heterogeneous mixture.
All right.
But if you leave them alone over time, hang on. Oh, okay, yeah. So two liquids are said to be miscible if when they are mixed, they remain as a heterogeneous mixture. However, if they're left alone for some time, miscible liquids, that's meant to be immiscible. That's where the error was. I apologize for the error.
That's okay.
So if you leave an immiscible mixture for a period of time, they're actually going to separate back into their layers according to their density.
Oh.
So an example of an immiscible mixture would be the oil and water.
Right. Yeah.
Yeah. Because the oil doesn't perfectly mix in with the water, does it?
No.
So back to the homogeneous solution, even a homogeneous solution is typically two different states, the same state. Well, by its nature, homo means same. So it means it has the same consistency.
Okay.
Yeah. So obviously the opposite is that when liquids mix to form a homogeneous liquid, they're said to be miscible.
Right. Okay.
So that comes back to the cordial example.
Okay.
Yeah. And immiscible liquids are generally separated using a separating funnel, as we can see on the right-hand side of the page, where essentially you turn, it's called a stopcock, you turn it until all the water comes out, and then you turn it off, and you have the kerosene oil left over.
Okay.
Do you have any questions?
No.
All right, cool. Cool. And then the final thing that we're going to cover is gravimetric analysis. So the gravimetric analysis of a molecule or something is the analysis of a mixture of its components by weight. So to provide you with an example of that, let's say I have a bucket, and in that bucket is nails, sand, rubber balls, and water. If I wanted to know, if I wanted to analyze the components by weight, I would actually measure how much of a percentage the nails are of the total mass.
Okay. Yeah.
So let's say the bucket weighs a kilogram, but my nails all up weigh 280 grams. So therefore, my nails are 28% of the total mass.
Oh, all right.
Yeah. But however, we're not going to actually do it using these macroscopic, so things that we can see, ideas. We're going to start applying them to actual chemicals.
All right.
Yeah. So I've kind of done an example here. So this is your first chemistry question, and we go through it together. But it asks, what is the percentage composition of calcium oxide? So percentage composition, back in the previous, in the first paragraph, is just the percentage of mass.
Yeah.
Which probably makes sense.
Yeah.
Okay, so we're trying to find what the percentage composition of calcium oxide. So we're going to find out how to actually name these compounds. So don't worry yet.
Yeah.
And hence, what is the mass of oxygen in a sample of 2.3 grams? So one thing that you are going to absolutely need throughout this module is your periodic table. But obviously, I have everything set out now, so you don't need to worry.
Mm-hmm.
So if we look at the periodic table, we can see obviously calcium oxide is made up of 1 calcium and 1 oxygen.
Yeah.
But to find the percentage composition, we have to analyze the components of calcium and oxygen by weight relative to the entire mass.
All right.
Does that make sense?
Yes.
Okay. So essentially the steps that you're going to do is that you're going to find the atomic mass of oxygen, which is on the periodic table, so don't fret.
Mm-hmm.
And you're going to find the atomic mass of calcium, and you're going to add them together to find the total mass.
Yeah.
And then to find the percentage composition of oxygen, it's just going to be the mass of oxygen over the total mass.
Yeah. Okay.
And to find the percentage of calcium, it's going to be the mass of calcium over the total mass.
All right.
Does that make sense?
Yeah.
Yeah. So we can see that if I picked up calcium oxide, 28.5% of that mass is going to come from oxygen, and 71.5% of that mass is going to come from the calcium.
Right.
Okay. So does the first part of that question make sense?
Yes.
All right, cool. So the second part of that question asks, what is the mass of oxygen in a sample of 2.3 grams? Well, this one's pretty straightforward, because if any sample of calcium oxide, the oxygen is 28.5% of that, then isn't the mass just going to be 28.5% of the 2.3?
Yeah.
Are you sure?
Yes.
Okay, cool. And you can see that I've put my answer in two significant figures.
Okay.
Can you tell me why I put it in two significant figures?
Because the value 2.3 has two significant figures.
Perfect. 100% right.
Yeah.
And that's kind of it.
Right.
So that's kind of a worked example. So on the next page, I have these things called concept checks. They're essentially exercises that you're kind of meant to work through regarding like the content that we've covered.
Okay.
Yeah. So I'll give you some time to complete the questions. You don't have to complete all of them if you don't want to, and we'll kind of go through the questions that you've done together.
All right.
So do you wish to tell me your answers as you go, or are you happy just to tell me them at the end?
I'll tell them as we go.
All right, no problem.
So question 1A is heterogeneous?
Yep. Did you say hetero or homo?
Hetero.
Air is homogeneous.
Homogeneous. Okay.
Do you know why air is homogeneous?
Because it's just one uniform substance?
Air is made up of many different types of gases that are all mixed together.
Mixed together. Yeah.
So it comes back to homo means same. So not only do we have the same state of matter being gas, because we have oxygen, nitrogen, carbon dioxide, we have everything in the air, but also air is it's pretty, as you said, uniform.
Yeah.
Like there's not a clump of air here that has more oxygen than over here.
Yeah.
So it's consistent. So therefore it will be homogeneous.
All right. Then B would be homogeneous as well.
Why do you think it's homogeneous?
Because they're sand. It's basically all in the same state of matter.
Mm. But is it consistent?
Not exactly.
Okay. So do you think it's a homogeneous or heterogeneous mixture?
Heterogeneous.
Good.
B would be homogeneous.
Oil?
I mean, yeah, C, sorry.
Okay. Oil is another heterogeneous mixture.
Oh, what?
It's okay.
Alright. Then D would be heterogeneous.
Good. Why would it be heterogeneous?
Because it's well, blood is made of different things, I guess. So they're all in different states of matter as well.
Perfect. In particular, blood contains dissolved oxygen, which is a gas.
Yeah.
Good job.
Question 2A. Filtration.
Yep.
And B would be is it Distillation? Oh no.
Distillation is when you boil something away.
Okay. Would it still be filtration or?
Yeah.
Yeah.
Filtration.
Okay.
But the idea is it's meant to make you think because you can actually use anything. So with the salt water, you could use distillation, you could use filtration, you could use evaporation. And for the cream and milk, well, the cream is much lighter than the milk, so it sits at the top, doesn't it?
Yeah.
So that means that you can remove the cream and milk through decantation, where you pour the milk away,
Yeah.
through filtration, as you said. You could even do it through sedimentation because, well, by nature, the cream sits above milk, doesn't it?
Yeah.
So don't necessarily think that there's only one way to remove something.
All right. And then 3. Density was mass over volume.
Yep.
So 1.35 over 0.5 times 1.2 times 0.95. So
Yep.
I'll calculate that. $2.37.
What are your units?
I forgot.
Okay. In science, we write things based on something called standard units.
Okay.
So, I'll get this up. So the way you wrote it was 1.35 grams
Yeah.
over 0.5 centimeters times 1.2 centimeters times 0.95 centimeters. And that gave you 2.37 or 23.7?
2.3, yeah, 2.37.
Okay, 2.37. And the units are going to be grams over centimeters times centimeters times centimeters. So your units are grams per cubic centimeter.
All right. Okay.
However, a much better way to put that is to keep everything in its proper units. So in science, we typically write mass in kilograms. And, well, we typically write length in meters.
Yeah.
So what do you think we will do then?
So wait, hang on. What was the question again?
Oh, you're asked to calculate the density.
Yeah. So it would be kilograms and then meters cubed.
Yeah, but you need to put this into kilograms.
Oh, okay. Yeah, yeah. All right.
Yeah.
Right. 0.0237 kilograms and then meters cubed.
Sort of. Would you like me to write it?
Yeah.
Okay. So, sorry, I was just kind of drinking water when you were doing that.
Okay.
Well, we want to keep in things in meters cubed. So, well, meters, hang on, no, grams per cubic meter, which is the actual idea for density. So if we go back to I won't get you to go back to it, I'll just snip and tool it across. Cool. So, it says here, the units of density are often expressed as the operation of the units of mass and volume. So that just means, well, mass divided by volume. So, for example, if mass is in kilograms and volume is in liters, then the unit of density will be kilograms per liters or kilograms liters to the -1. So because we were given centimeters, yeah, you're right. You can write grams per cubic meter, so grams divided by meters cubed, but you can also write it in kilograms per liter or kilograms per cubic meter. Does that make sense?
Yeah. Okay.
Oh, your answer is correct if if you're unsure.
All right.
Yeah, you just need to make sure that you write this.
Okay.
Actually, that, yeah. Grams per cubic
So
centimeter.
is that unit of measurement called grams per centimeter cubed?
Yes.
Right. Okay. All right. So question 4.
Yep.
To separate the iron filings, we would get a magnet.
Mm-hmm.
Yeah, and then separate all of them out of the water, sand, and rocks. Then you would sieve the water and sand to separate the rocks.
Mm-hmm.
And you can distillation is the boiling, right?
Beg your pardon?
Distillation is when you boil to separate the substances, right?
Yeah, but you keep the two substances, whilst evaporation is the water will escape.
Yeah, so you would distill the water and sand.
Perfect. Full marks.
Yeah. And question 5.
So for 5, you actually need to look at your periodic table. So I sent that to you earlier.
Yeah. Give me a second.
All good.
All right. So magnesium chloride.
Yep.
Magnesium has an atomic mass of 24.31.
Good. So I'll write it here I'll do it with you for the first one.
Yeah. And then chlorine has atomic mass of 35.45.
Okay.
So since there's 2 chlorine particles, you would double that amount,
Okay.
which is 70.9. And so you add those values together, 24.31 and 70.9.
So mass of MgCl2.
Yep. And so that would be 95.21.
Yep.
And so the mass percentage composition of magnesium would be 24.31 over 95.21 times 100.
Yep.
And then for chlorine, it would be 70.9 over 95.21 times 100.
Perfect. Yeah, that's it. And just a question, how many significant figures would you leave this in?
4.
Yeah, because everything on the periodic table is the 4 significant figures.
Yeah.
Good work.
Thank you. So for B, it would be sodium and sulfate. So sulfur and oxygen.
Yep.
And so the atomic mass of sodium would be 22.99.
Yep.
And the
I'm not writing this one in case. Yeah.
Yeah. That's fine. The atomic mass of sulfur would be if I can find.
It's number 16.
Yeah, 32.07. And oxygen would be 16. Since there's 4 oxygen particles, that you would multiply 16 by 4.
Yep.
And then sodium by 2 because there's 2 sodium particles.
Good. So what's your atomic mass for the whole thing?
The whole thing would be sorry, give me a second.
All good.
$142.05.
Good. So now you have to find the percentage compositions.
For sodium, it would be 45.98 over 142.05 times 100. For sulfur, it would be 32.07 over 142.05 times 100.
Yep.
And for oxygen, it would be 64 over 142.05 times 100.
Yeah, and once again, how many significant figures would you leave all those to when you actually calculated them?
4. Oh, wait, 5.
4.
4. Oh, okay.
It's still 4.
Right.
Because your significant figures isn't dependent on the 142.05. It's dependent on your starting things.
Okay.
And everything on the periodic table, those initial masses that you had, as you can see, they all have 4 significant figures.
Yeah.
You don't have to do part C, you can do that for homework if you wish.
All right. Okay. So 6.
I would like you to do question 6 and question, oh no, we'll just do question 6 and move on.
All right. Okay. The percentage composition of this compound. I guess, is it the percentage composition of each element?
Yes.
Yeah. So basically it would be 5.217 over 8.657 times 100 for carbon,
Yep.
and then 0.9620 over 8.657 times 100 for hydrogen, and 2.478 over 8.657 times 100 over for oxygen.
Yep, perfect. You can see how repetitive these more simple questions are.
Yeah.
Would you like to do question 8? That's more of a challenge question, or would you like to move on?
I'll try and do it.
Okay.
Isn't it just 3 3.63 over 500?
Yeah, that's what I was thinking when I read it. I thought this
Yeah.
was a challenge question. Uh-oh.
Uh,
Oh well. I guess you got me that one. Alright, yeah, so that's it. You want to move on?
Yeah.
Alright, cool. If we run out of like things to do for the lesson, we can go back to that. Question 7. That's a good question.
Yeah.
Alright, so now this second dot point, we're actually going to be looking at the periodic table now. So you've already used the periodic table to actually look at the atomic mass of certain things. But now we're actually going to be looking at the periodic table into, well, what the heck it actually is, which is very nice. So on the periodic table, I like this feature of the periodic table very nice because it actually groups all the different groups of elements together.
Mm-hmm.
So we'll be going over like the alkaline earth metals and all that on the upcoming pages. But for now, well, what is the periodic table? The periodic table is simply an ordered compilation of all known elements according to their chemical properties. And we're going to find out more about how they're actually ordered later on in this module.
Okay.
So for now, all you need to know about the periodic table is 4 things, and you can see this on your periodic table. We have the number, the element symbol, the atomic mass, and, well, the name. So you don't necessarily need to worry about the atomic number now. We'll worry about that when we get to it. But you've used the periodic table already to use the atomic mass, so you know where it is.
Yeah.
Cool. No questions?
No.
All right, good. So now we're actually going to like talk about the actual idea of the table. So the periodic table is made up of, well, rows and columns. And it's not a coincidence how these rows and columns actually align. There's actually very specific reasons. So firstly, we're going to talk about the periods. So the periods are essentially the rows of the periodic table. As you can see on your copy of the periodic table, they increase in atomic number from left to right because that's the order the periodic table goes. And the rule of actually what the periodic table is, so what each period, means how many electron shells are in that period. So this is where I actually explain what the sequence of the atom is, briefly, but we will go over it because it's actually in the syllabus later on. So, do you know the parts of the atom?
Yeah.
Okay. Can you tell me what the parts are?
The nucleus, which contains the neutrons and protons,
Good.
and then the electron shells surrounding the nucleus, which contain the electrons.
Good. But are you aware that you can have more than one electron shell?
Yeah.
Oh, perfect. So you already know this.
Yeah.
All right. So essentially what it means, so the first shell, are you aware that it can only hold 2 electrons?
Yeah.
All right.
And
And then the next shell begins, which can hold 8 electrons and so on and so forth.
yeah.
But we cover this, so you don't necessarily need to be worried. But I'm really impressed with your background and knowledge.
Thank you.
I didn't even share my screen for my little dodgy diagram. There you go. So that's my little dodgy diagram. I was going to draw in shells. But yeah, so how it actually works on the periodic table is that the number, well, the row you are indicates how many shells you have.
Yeah.
And then secondly, the groups are the columns of the periodic table. So what is different from a group to a period is that whilst the period tells you how many shells you have, the groups tell you how many electrons you have in your shell, which is called your valence shell.
Mm-hmm.
So you probably, or you may already know this, but if we look at our periodic table, we can see that, well, lithium, I'm going to start with the second period.
Mm-hmm.
Lithium, it is on the first group, so it would have 1 electron in its valence shell, which is going to be the second shell. Berylluminum would have 2 electrons because it's the second group,
Yep.
so on and so forth. Oxygen would have 6 in its outer shell, and neon would have 8. That would have a complete outer shell.
Yeah.
Any questions?
No.
All right, cool. One thing that we're going to look at, so this first lesson, or this first inquiry question, is really annoying because I have to kind of like half explain things because they can come back to them later. But yeah, so kind of everything I say now, we're going to cover again
Okay.
a couple times, but yeah. So where an element is regarding its period and group gives it its various chemical and physical properties. So for example, group 1 elements have 1 electron in their valence shell, so they're highly reactive. So that's an example of hydrogen. You are aware that hydrogen is burns very, very quickly with oxygen.
Yeah.
So like when they used to use blimps, they'll fill them up with hydrogen because and then the blimp went boom in America, and that was a casualty. But on the other side of the periodic table, group 8, they have a full shell. They're called the noble gases. And because they have a full shell, they don't need to react with anyone to get a full outer shell of electrons. So they're called stable.
Okay. Yeah.
Types of materials or elements is called metals, metalloids, and non-metals. So the idea of metals, metalloids, and non-metals is the general physical properties. So as we can see in the image, everything that is white is a metal. The blue little staircase is the list of metalloids, and then everything that is pink is a non-metal.
Yeah.
So the general properties of metals is that they're good conductors of heat and electricity. They're malleable and ductile. Do you know what malleable and ductile means?
Malleable means it can be bent. And ductile, I'm not exactly sure.
Okay, ductile is the ability for a material to be drawn into thin wires.
Okay.
So like it can be kind of stretched out.
Yeah. All right.
Yeah. Okay, so that's metals. And then conversely for non-metals, well, non-metals are basically the exact opposite. So they don't conduct heat and electricity. Actually, they're called insulators of heat and electricity. They're brittle, they're usually dull, so they're not shiny, and the vast majority of them are liquids and gases.
Yeah.
And then we have the in-betweeners, the ones that can't make up their minds. These are called metalloids or semi-metals. So the reason why they're metalloids and not one or the other is because kind of the way it's come out that they have properties of both. So like for example, they may conduct electricity, but they may be brittle.
All right. Yeah.
Be shiny, but they may be shiny, but there may be a gas at room temperature.
Okay.
So the actual list of elements that are metalloids are as follows. So boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. So you don't necessarily need to memorize those elements, but you need to be aware of what they actually are.
Okay.
Yeah. And then on the next page, I actually have a breakdown of all the different groups. So firstly, we have the alkali metals, which is group 1. So all the electrons have, all the elements have one valence electron. So it just means one electron in the outer shell, as we already established. So physical properties, they're soft, they can be cut with a knife. They're lustrous, so they're shiny. They have low densities. They conduct heat and electricity very well, and they have a very low melting point.
Okay.
And then, so I'm just going to read these off, so I'll just continue. I don't understand anything. With chemical properties, they're highly reactive, which means that they want to react with things because they only have one electron. Vigorous exothermic reaction with water. Don't worry about that just yet. All it means is that when it reacts with water, it releases heat.
Okay.
But once again, we'll cover this later on. And okay, so next we have alkali earth metals, which is group 2. So logically, it's going to have 2 valence electrons. Physical properties, they're lustrous, metallic solids, high thermal and electrical conductivity. They're more dense than alkali metals though, and they have higher melting points, boiling points, and are harder. So you can see that just between these two different groups, the chemical properties, the chemical properties and the physical properties are very similar.
Yeah.
And that's because the only thing that's really separating these two different, lithium and beryllium, is just one electron. But that one electron has some very big impact because when we get to the other side of the periodic table, it's actually going to be very, very different properties.
All right.
Yeah. So next is the transition metals. So that's groups number 3 to 12. And the reason why these ones are a little bit different, and I'll actually get up my periodic table, is because, so can I write on here? No, I can't. Yes, I can. Cool. Draw. All right. So this one is group 1, this is group 2, and the actual, all of these metals are going to also have 2 electrons.
All right.
Yeah. And well, the reason for it is that we would actually run out of electrons if we continued. But so that's kind of the logic behind it. So if we had 3, 4, 5, 6, 7, 8, 9, 10 all the way to here, then we would have 18 electrons in total, which doesn't really work, does it?
No, yeah.
Yeah. So that's why these ones are actually put at like a little divot.
All right.
Yeah. So all of these, so from here to here, They all have typically 2 electrons in the outer shell. And you can assume that there will typically be 2 electrons in the outer shell unless you're told otherwise. And you'll be told explicitly otherwise.
All right.
So you don't really need to worry about it. Continuing, we have the halogens, which are group 17. So that is this group here. 7 electrons in their outer shell, which means that they're just missing 1. So,
Yeah.
3, 4. Should make that more visible. 7. Cool. So this is where the actual the properties start to change. So firstly, physical properties, they're non-metals. Their melting and boiling points are very low, sorry. And the reason why they're very low is because all of these elements, they're all typically gases at room temperature.
Okay.
So if they're gases, that means that their boiling point is very low. Furthermore, the halogens like to be special. They actually change state when you're going down. So this is a gas, this is a gas, and then this is a liquid, and this is a solid. How fun.
Yeah.
But once again, it's just kind of demonstrating that it gets weird.
Yeah. Okay.
Yeah. What more? They're poor thermal and electrical conductors, which differs to these guys over here who love to conduct electricity, don't they?
Yeah.
Yep. So you can see that it's kind of like the exact opposite.
Yeah.
Unpleasant odors, very toxic. So we have chemical properties, so they're highly reactive. Don't worry so much about forms ions of -1 charge. Once again, we will cover it. And form diatomic molecules. Once again, we will cover it. And then finally, we have noble gases. So noble gases are these cool guys over here. And what is very special about them is that they have 8 electrons in their outer shell. And when they have 8 electrons, what that essentially means is that their electron shells are full.
Okay.
But because they're full, they don't actually want to react with any other, because as we'll learn, the whole idea about chemical reactions is that it involves the exchange of electrons.
Yeah.
You may have come across it, I'm not necessarily sure.
Yeah.
Okay, cool. So this is what makes the noble gases so special. So physical properties, they're all gases. They all have really low boiling points and they all have very low densities. Chemical properties, they're highly unreactive because, well, they don't want to have full shells. They're mostly present as monatomic gases because, well, if they have a full shell, then they can't join to make like O2, for example.
All right.
Once again, well, yeah. But yeah. And because they're unreactive, they very rarely form compounds, although you can actually stick them together with other elements in labs and stuff like that.
Yeah.
Yep. And that's essentially it for theory. So we just have this concept check and we'll be done.
Oh, all right.
Do you have any questions?
No.
Okay. How are you feeling regarding the content?
It's all right. I got most of it.
Okay.
Yeah.
When you said most of it, do you want to go over anything?
Not really. It's more, I was confused on physical and chemical properties at first, but I got it, and then the later content was a bit easier to understand.
Okay.
Yeah.
All right. Cool. If you need anything, just let me know.
Yeah. Yeah.
I just attached your. However, I will resend it because I accidentally included a question in there that shouldn't be there. So I'll do that one quickly.
Yep. Okay. For the first question, A, carbon, it's in group 4.
Yep.
So what would it, so since it's a non-metal, would it have the properties of a non-metal?
Good. Yeah.
Yeah. All right. Okay. So that would be they don't conduct heat or electricity.
Or not that they don't conduct it, they don't conduct it well.
Yeah. All right. And what does it mean? I forgot to ask. What does it mean when substances are brittle?
It's just brittle.
But what?
Yeah, you just say it's brittle.
Oh. All right. Okay. All right.
Yeah, that's actually the term for it, just brittle. It's just the opposite of ductile.
Yeah. Okay.
Also, I'm having some formatting issues with your homework, so I'll send it across when everything's nice.
Okay.
Do you have any questions?
No, I'm just writing down the my answers into my book.
Do you have any questions?
No, I just finished question 1. Oh, wait, I didn't do E and F, but I did up to copper.
You don't have to do
So-
any more if you don't wish to.
Okay. So for carbon, it's a group 4 non-metal. So it's an insulator
Yes.
and it's brittle.
Mm-hmm.
B, sodium,
Yep.
it's alkali metal,
Mhm.
which means it's highly reactive with water and oxygen.
Mhm.
It's soft, has a low melting point,
Mhm.
and a low density. It's also a good conductor.
Yep. That's really good.
Fluorine is a halogen, and is gaseous. It's toxic, has an unpleasant odor, highly reactive, but it's not a good conductor.
Yep. Good.
Copper is a transition metal, so it's hard, lustrous, less reactive than alkali metals, but still reactive, and has a high melting point.
Good.
That's all I did. So
No problem. We have 10 minutes left. Would you like to continue doing the questions so you don't have to do them for homework, or would you like to maybe look at your homework, start your homework, whatever?
I'll finish off this question.
Okay, no problem.
Yeah. So gold is a transition metal, so it has the same chemical properties as copper. And so it's hard, it's lustrous, it has a high melting point and is less reactive than alkali metals, but still reactive. And hydrogen is an alkali metal, so it has the same chemical properties as sodium. So it's a good conductor, it's highly reactive with water and oxygen.
Yep.
It's soft, it has a low melting point, and a low density.
Yeah. So that was a little bit repetitive towards the end. Would you agree?
Yeah.
But the reason why you actually gonna have to memorize all these properties
Yeah.
because you can actually be asked on differentiate between alkali metal, alkali earth, transition metal, halogen, noble gas.
Yeah.
Yeah. So yeah, this lesson was it was an introduction.
All right.
We didn't do some questions in the prior concept check, but I want to double check 7 because
Okay, yeah.
you can't do question 7. I apologize for that.
That's okay.
Yeah, that is an entirely different module, so I don't know how that got in there. So yeah, you don't have any more questions. You don't have anything else, I believe.
Yeah.
All right, cool. So we have a couple more minutes. Would you like to maybe look at your homework, or would you be interested in looking at some more content for next week?
I'll look at my homework.
Okay.
Yeah. Could we quickly go over miscible and immiscible substances,
Okay.
liquids?
The idea with miscible liquids um, is that, well, okay, let's begin with immiscible. So if something is immiscible, that means that when they're mixed, they're a heterogeneous mixture. They don't properly mix together.
Okay.
If we were to let an immiscible mixture rest over time, it's going to separate into its two substances like oil and water.
Yeah.
Whereas for a miscible mixture, such as some like a little bit of salt and water, the salt is going to stay dissolved in the water.
All right.
Yeah, like not too much salt that it sinks to the bottom, just like a little bit of salt.
Yeah. All right.
Does that make sense?
The immiscible is heterogeneous, and miscible is homogeneous.
Yes, but remember, immiscible and miscible only apply to liquids mixtures.
All right. Okay. Okay.
Yeah,
Thank you.
no problem. I'm going to end our lesson now, if it suits you, because I have another. Yeah, no problem. Yeah. So, um,
All right. That's fine.
start wrapping it up now. If you have any questions, actually, I didn't give you my contact details, so I'll put my phone number in the chat.
Okay.
Any questions, please contact me and let me know, and I'll get back to you.
All right. Okay. Thank you.
No problem. Bye.
Bye.